Okay, so anyway, let's get started. I'm going to talk about segmentation, and both slides from many fellows here, as you can see. And this is just oh, sorry, I was not even, let's see. Why is, okay. Yeah. This is some of this example, just give us some thoughts that why segmentation or why image understanding is so difficult. So what do you see, by the way? I'm sure you see both. Actually, the more you look at that, probably you see more stuffs here. But of course, you can see this gentleman here, this old guy here, with his hand here. Or you can also see this as a dog. There's old man here, this lady here, and there's some leaves or trees at the back, like bushes. And there's also faces everywhere. And for segmentation, it's just the concept is very simple. Right? We just want to have some object, like some background, foreground, and we want to extract the interest objects, like the outline from the background, and this is some of this ideal segmentation result, right? So if we have images like this, so if we think of we are human, potentially we like to be able to segment result like this, right? This is each of these is the buffalo, I guess, and then maybe we segment these two boys here with the guns and so on and so forth. And also there's some application known as superpixels that we'll talk about that later on. That in the sense that you carve over segment, then each of this tiny region here will be we call it a superpixel, and we can process that more efficiently on the superpixel sometime than process the individual pixels. And yeah, we can have further processing afterward. And this and of course we can also use segmentation to extract features like for example, we know that this is a train here, so for the object we know that this is the object here, and we try to extract features only on the objects but not outside the object. And there's some actually we will talk about this algorithm here, this is pretty famous algorithm, and this is this one, we will talk about this one as well, actually, she and Malik. This is an example for superpixel, as I mentioned. There's some more example application. For example, you can use segmentation to just, I can extract the foreground, and then the background I can put in something else. Actually, that use a lot in the studios, right? So you have the blue screen at the back, and then you put lots of different background, when you in the movie there, that all the fake backgrounds is attached to the blue screen, and also we mentioned some. Actually, we didn't mention that. I will mention a little bit, for example, for object detection, we can have region proposals. And segmentation can be used to generate these region proposals, right? For example, this selective search is used to generate this region proposal. That's and this work I don't remember but that's also ways to generate region proposals. But we are not going to that. We're only going to talk about segmentation today. And of course, one way to think of segmentation is it's actually just a special case of clustering. So you have pixels, you want to cluster them together, and there's some challenges such as how do we determine pixels are similar. Of course, when you cluster, you want to cluster stuff that's similar, right? So we need to design what is the distance measure to say like 2 pixels or like 2 patches are similar to each other, and how to compute that efficiently also, like, and let's skip some of these. There's also like more of this example for application for segmentation, and also like actually let me just go directly to some of this algorithm. But before that, let's look into like something from psychology, that this Gestalt idea that like saying that like the collection is more important than individual. Like basically the whole is greater than the sum of its part. This is this kind of illusion. Like we I think all of you like saw that before, right? This kind of illusion, and if you think of this as a segmentation problem, it will be very difficult. Right? How do we actually able to segment this like triangle out like with a machine or like computer? And there's some more interesting example. For example, what do you see here? What do you think this thing is? Like this thing is, or like what do I say? I mean, maybe multiple objects here, or like we have some y, or like something like k, or like so I don't know what do you see, but with this I'm quite sure like what you will see now. So I mean it's interesting, like with this occlusion sometimes like you just interpret stuff like completely differently, and this is another interesting example. So what do you see again? Like can you see anything? Like and now what do you see? I don't know about you. For me, I see five lines here. Yeah, but if you think of that, like we really have like a strong prior in our brain somehow, and of course I see the lines because I know this Arabic numbers, digits, but yeah. Anyway, it's something kind of interesting. This is another example. Definitely, you saw that before, and this is another very interesting example. A very challenging kind of like from scene understanding of like object recognition. So human able to like, I'm sure like all of you guys can see the dog here. I'm not sure it's a dog or like, yeah, probably it's a dog, and then over there's a tree here, some shadow, but it's quite amazing like how we're able to figure that out. So anyway, like get into some technical stuff. Like we probably cannot tackle this Gestalt, that kind of like illusion for most. Actually, I think like for, yeah, I can say almost all segmentation algorithm yet. But even maybe like some deep learning like stuff. But let's look into some more classic approaches and also some simpler application, a simpler example that some. This is another fun picture, but let's go ahead anyway. So so as I said, like the segmentation problem, you can think of just like a kind of special case for clustering, right? So to think of like some of the desirable properties for a good clustering algorithms, it needs to be like scalable, like in terms of both time and space, and should deal with like different data type, like, and that hopefully doesn't need lots of like domain knowledge, and it will be interoperable and usability optional. Actually, I'm not quite sure what does that mean. Oh no, interpretable. I'm sorry. Yeah, interpretable. Yeah, it makes sense. Interpretable and usable. Yeah, at least interpretable I understand. Usability optional. Yeah, I guess in the sense that you can add some prior knowledge there. So, but let's go to some classic method here. So let's think of like a very simple clustering problem. So we want to cluster things together and just group stuff that is similar to each other. So one of these approaches we may use is think of like a bottom-up approach. Just start looking into like two objects that's closest together, then you just cluster them together and continue to do that. And then you look into like when they are grouped together, you look at the closest group, then you group them together, and so on and so on. And this is a so-called agglomerative like clustering. So you to begin with, you can say like every point is a cluster, and then you just start to find the most similar one, and then you pair them together, then you merge them together to form a parent cluster, and then you repeat and repeat again. So as I mentioned, like there's one major problem. Like question we need to answer first is like how do we determine like the similarity between clusters. So there's lots of different options we can pick. For example, like average distance between points, like maybe the maximum distance or minimum distance, or like distance between mean or medians and so on. Method in this case, and also like we need to determine how many clusters we want, right? So and I guess this is fast to the conclusion, but I will give an example. So here, if you think of the most, I should say, basic approach, basic implementation, naive implementation of agglomerative clustering, then some of the problems, if you just implement as what I described, it may not scale well. The one time will be like n cube, order of n cube. Of the n is basically the number of like in our case would be our number of pixels there, and it can start with local optimum, and of course I will still need to choose number of cluster and so on, and also may have some imbalance cluster, but of course the idea is simple, like easy to implement, and so on and so forth, have some this kind of like advantages. And actually, as I mentioned, I like to talk about this work is by, I don't know how to pronounce the name basically, I won't try to. So it's a pretty famous work, like over 5,000 citations, I believe. So you can think of that as this kind of agglomerative, how do you say that again? Agglomerative clustering approach. So this is some of the results, but let's look at like how they do it first. So as I mentioned, I basically just merge from bottom up way, but we need to kind of figure out several questions. As we mentioned earlier, how do we determine the distance between the clusters? So what they do is basically you consider each of the pixels as a node in a graph. Then you can form a graph somehow. After you form a graph, then you can then determine the weight between each of the edges there. I will say more about the weight. Let's say you have the weight there, and then you can think of like the algorithm. Maybe you start with the graph will be completely disconnected at the beginning. There's no edges. Then you continue to build edges out of that. And let's go more detail into that. So first of all, like we mentioned that like we need to design like the distance. Okay, I haven't even specified distance yet, but let's say we have the distance now. We'll need to determine whether we want to merge or not merging a cluster. Let's say we have an edge now. Let's say we say like there's two cluster here. We have an edge connecting them. We need to determine whether we want to merge them together as a bigger cluster. So the authors propose a very simple kind of they call it predicate or like a criteria to determine that. So basically, just say like whether the internal difference between the cluster if it's like bigger than the external difference or like the difference between the two clusters. If so, then we just merge them. So then we need to say, okay, we just defer this question, right? We need to determine what do we mean by this internal difference and the external difference between the clusters. So the external difference can be like this. So let's say basically what they define. So let's say we have the graph here. We have the weight for weight is basically the weight of each of the edges, and then consider the two different clusters there. We just see like what's the minimum distance between the two clusters. Namely, like we look at each of the vertices inside the clusters and look at like just find the one that is shortest, and that will be the difference that they consider. And then like now for the internal difference or the internal how do we call it again? How do we call that? Internal difference of the cluster. We basically we will have expression like this. We'll look at like for example for this cluster here, we'll just see like what's the maximum distance between like any two nodes there. And of course, like, inside the cluster, they should be connected, right? So therefore, like if they are not connected, the maximum distance will be infinite or something. So the maximum distance from the clusters, and they also add the terms here is basically just an adjustment. So this can be used to make the internal clusters to be bigger. If the internal cluster is bigger, then you can have like less number of clusters, right? Eventually, if the algorithm goes, because there's more likely you will merge clusters together. And of course, if you say the internal difference of the two clusters, we just compute the internal difference in the first cluster and the internal difference in the second cluster, and then they take the minimum among these two. That would be the internal difference of the clusters, IN C1 and C2. And as I mentioned, they would decide to merge the two clusters if this diff C1, C2 is less than in C1, C2. And as I mentioned, they have this K over C here. It's basically just adjusting like how likely you're going to, how many clusters do you have. So if you have a large K, then you make the internal difference to be kind of artificially bigger, so therefore more likely to merge clusters. So you have less number of clusters. And then the algorithm is basically it's pretty simple, as I mentioned. So first, you let's say if you have all the vertices here, and then all the vertices, you will have some potential edges there, and then and you sort all the edges to see which is the shortest one. So you just sort them ascendingly. So you're starting with the shortest one, and then before that, you will consider all of these vertices has its own cluster. So then you start with the shortest edges. Actually, I think I said something wrong earlier. So the graph supposing is to start with kind of all connected, but you treat yeah, I mean, the graph to start with is connected, and all vertices is treated as its own cluster, but then you slowly merge them together. So anyway, so let's continue this first. So so as I mentioned, you start with the shortest edges, right? Then you need to decide whether you want to merge them or not. I mean, you want to merge the two ends of the cluster or not. So if you start with the two shortest edges, if they already merged, then you have nothing to do, right? So then you don't need to do anything. Then you look into the another edges. You just continue to look at the longer edges. So otherwise, you just see like what we kind of mentioned earlier. Right? You see like whether these two clusters actually satisfy the condition we set the internal difference is bigger than the external difference. If so, we just merge them together. So therefore, it's actually a pretty simple algorithm. So of course, we still differ some of these details here. Say how do we build the graph at the beginning, and what are the weights there? So there are like several options you can do. For example, like one option is a grid graph weight. So basically, you just have like all the pixels are connected like that. So you just connect to all, it's like 8 labels there, and then yeah, actually just connect to all 4 labels there. Like that's not 8. So and then like for the weight there will be simply the difference of the intensity. So therefore, like if it's more closer than in terms of intensity, then it's more likely they merge together, right? So it's obvious. So another approach is like this Lewis label graph weights. So in that sense, you map into a different feature space. So you can have like, you can even use different class space. You can try different class space, but let's say just use RGB here. So therefore, each pixel will be like 5 dimensions, right? The color space, including the coordinates, so 5 dimensions there. Then you can determine for each pixel and try to connect to all the other, not all, but like for each of the pixels to see like which pixels is closest to any of these pixels. And then you pick here, like they should only pick the 10 newest labels for each of the pixels in this high dimensional space and build a graph. So of course you can make more connection there, but then like will be a higher complexity. And this is some of the results. This is like based on the grid graph approach. That the first one will have like a result like this, and that's another one. This is like based on the Lewis label graph approach. So and that's the algorithm like clustering, and other like very famous clustering methods, the k-mean. So I'm sure like many of you heard of that before. So you have like, let's say, input image like this. So if you think of that, if you look at the histogram, it will be like this, right? And then like k-mean will be so actually for this one it's very easy to cluster because you can say like the intensity is below that is one cluster, above that is another cluster, and it's completely clustered perfectly, or like segmented perfectly. But like if we have noise, then it will be a little bit complicated, right? For example, we have a noise here, so we cannot just simply cluster, like, or actually we can still do that, kind of, but we need to determine where's the mean here, for example. So actually you can do more or less very similar as here, right? So for here, you can say it's exactly this value. It's like one cluster or like one segment. If I have, I mean, the intensity is at this value, then I'm in another segment here. In this intensity, there will be another segment outside. For here, then what very simple extension will be like, maybe I will pick a center or kind of like a representation for each of the cluster. Like, for example, I also have 3 clusters here, like, and put the intensity here, here, and here. say like whenever like, it's closer, for example, if I pixel I have closer to this representation here, then I will put in that cluster, right? So I can just also like use 3 values here. But then like a question is like where do I pick the representation or representative there? Of course, like here, like from this vector, it's very simple. I just pick the peak, or let's say, right? So in general, what should we do? Like we can do use this so-called k-mean algorithm, right? So actually, how many of you already know k-means? How can you just say that? Actually, k-means is again like some of these I would say universal truth, including like something else like for example EM like expectation. I mean this kind of like stuff like is so true that like no matter which community you are, you eventually will discover that. For example, like people in for example computer science or like machine learning, they call it k-means, but there's people also study like source coding in electrical engineering or like in more like in communication, source coding like will be source compression. They call it like Neumax. It's basically the same algorithm. But the idea is extremely simple, eh? So by the way, how you will do that? Like this is like so simple that I think like even you don't look at that, you can guess like how do you do it, right? So let's say you have like some samples here. So what do you do? So I want to, as I mentioned, I want to find a representation, right? Somehow I have a representation for this guy. So say that like if closer than this, any points, if closer to one of the representation, it will group into that cluster. So but how do you determine the representation? Just from this simple example here. So or I would say like if I have some representation, how do you make it better? So let's say if I start with I'll start with something like here, say to represent this one here, I have like here represent this one here, let's say, or like here represent this one. What do you think? Like how should I kind of maybe update these representations so that like or like these cluster centers, so that like I will have a better kind of clustering or segmentation. Yes. Oh, sorry. Like why yes. Yeah. Okay. So as I mentioned, I can cluster here, like clustering center here, cluster center here, here. So what can I do? Maybe I can update this center so that like it will be kind of better. Or actually, if I give another example, like if I have cluster center here, and here, is that good? Like probably it's not too good, right? If it's in particular, if I have cluster center here, then it looks like that like I will include some of this point here in this cluster because this point here is closer to here than this here. Then I will have like this cluster is pretty weird that like have the boundaries like in the kind of like here, like it looks like it's definitely not. So okay, I'll just answer it myself. So let's say you start with something here, oh, this is not right. So maybe I pick this one again. Like if I start with something here and here and here, let's say. So what I may do is maybe first of all, like, okay, if I have these three cluster centers now, so then like I now can determine like, which are my members, right, inside the clusters. So as you can see, like these people are in the cluster, and actually these people are in this cluster, and these people are in this cluster here. So then afterward, like maybe I can say, is this a good representation for this cluster here? Maybe not, right? You expect that a good representation should be more or less in the center, right? So therefore, like I probably want to take the centroid of these people here, right? So maybe I can compute the centroid of this guy. So if I compute the centroid of all these fellows in this cluster, I probably move to here. So now I'll move to here. So I may do the same thing like for this guy here. Then maybe I will move more or less to on this side, and I can also like for these people maybe doesn't move, like it will be there somewhere here. So actually, as you can see, I can repeat this step here, right? So if I repeat that, next time I try to look for the whose belongs to which cluster, then okay, next time it's pretty nice. It looks like that. Now if this is the cluster center, this is the cluster center. Now it looks like the middle is somewhere here. So now this cluster does not cover like these fellows. Happen it shouldn't belongs to this cluster, and probably if I will take a middle somewhere here, maybe, right? If I have the cluster center here, so this should be my new cluster and new cluster here. And you see an improvement. Actually, it makes sense, right? And I can repeat the same step. So for this guy, again, like, this is probably not a good representation for these fellows here, right? Why I should represent this fellow with somewhere so far away from its center? So I can compare the centroid for this guy. So I will move to somewhere here, right? So now I will have like the new representation is here, the cluster center is here. Then for this fellow, cluster center may move to probably somewhere more in the middle here, and this move to somewhere here maybe. So as you can see, like this basically the K-mean algorithm or the long mass algorithm. So it's just like an iterative algorithm that you keep updating the location of cluster center. First, if you have a initial cluster centers, then you just try to find like for each of these fellows which clusters they belong to. Then you have this. You group all the memberships here for all the people there. Then within the clusters, then you can like compute the centroid again, and then you update the cluster center and so on and so forth. So this is the K-mean algorithm, and so this is just the equation to explain that. So this just finding the membership. I find the closest center there, and then this will compute the new center. And then I just iterate. So there's some Java demo. I probably won't click that. Or like just illustrate like if you have some determine some like center there. Oh, maybe I will click it anyway. Let's see if I. Should have connection though. Yeah, actually I have. This is, as you can see, so old school. This is using Java applet. I think I need to. So there's some place I should click to activate Java probably. Yeah. maybe try. Yeah, I guess I'll just leave you guys if you're interested to look at that. But anyways, I assume very simple demo. So so there's just more example of k-mean clustering. So now this is an actual application for segmentation. So let's say I just use color space for, I mean, in this case, actually just one value in density. So I can pick like 2 clusters, just in terms of density, I get something like that. And like 3 clusters have something like this. And there's some algorithms done like k-mean plus plus. It's basically just a small modification by just down the volume here. So basically just like I mean like in the early version, like we didn't specify like where we picked the initial k centers, right? This one just a small modification so that like you want to pick the k centers to be more diverse. So each time you pick a new center, it's kind of like with probability kind of like proportional to the distance away from those centers. So you want to pick the centers, new centers to be farther away, and that's about it. Oops, again, like. And in terms of feature space, as I mentioned, like we can use intensity, but of course, we can also like as you see like in the other algorithm we mentioned earlier that we can use like color space, and also like we can have like high dimensions. Like actually, for example, like we can include location into that, or even use feature space. So for example, like you can map into use different filters and like use a patch of that filters and like so for example, like if I have a filter bank of 24 filters, then if I take like a pixel there, I will just apply the filters to the neighborhood of that pixels. Then I will have like 24 vectors, right? So I can also like do kind of segmentation in this 24-dimensional space. So that's that's the other one I mentioned. You can use intensity plus the position as well. So earlier we just used the intensity, but of course you can, if you also include the position, that makes a little bit sense because you want to say like things like close together is in the same segment. There's also like some more results here, just demonstrating this k-mean clustering. And actually, this is not just the k-mean problem, but you see like many of these algorithms, you need to first determine how many clusters you have. So one way you kind of like to determine that, like you can just like do it like afterwards. So you just try different number of clusters, and then like you can apply some kind of objective, like to say, for example, okay, that's not a possibility to design the objective function. So, but let's say if you have some kind of objective that you have determined, you just want to look at like okay, whether you have a clean or like elbow, a knee or like elbow kind of like corner here. So then in that case, probably is k is equal to 2 is a good one. Like you have a good job of like your objective cost like from 1 to 2, then you don't like change much afterward. And k-mean is kind of I guess like the simple one is like it's kind of like, I mean, the nice thing is like it's kind of simple, right? And but that's knowing that like all this approach, right, because it's more or less a linear approach, it's actually a linear approach. Therefore, like you cannot kind of cluster problem like data like this. So if you have some other like nonlinear clustering algorithms, you will be able to like segment these two data sets here. But for k-means, it's just impossible to do that. And another algorithm is kind of also have a similar flavor. Is the mean shift algorithm that actually let me go to this I guess a pictorial explanation is better. So you again are trying to do clustering here. So and you want to determine like whether like all these data points here are in the same cluster. So it's similar to k-mean. Like you can start instead of like looking at like a entire global region, you just look at a kind of like a local. For example, like let's say like in k-mean, we first determine like a cluster center right here. We also like determine one cluster center here, but in k-mean, we kind of like this cluster center will be have effect globally. So each data points, we're trying to see like whether it's like closer to any of these cluster center that's even is like far away. But for mean shift here, we'll just have this local effect. So for each of these cluster center, we just look at the local region here, like in this neighborhood, and then like so these guys like in the neighborhood will be in the same cluster. So then like similar to the k-mean, then we can say, okay, if these are the data in the cluster, then this is probably not a very good representation. We want to use the central instead, so we can compute the center. Then you basically have the center. You shift to the new center, then you have a new region of your membership, right? So then you can repeat that. Then you have this so-called mean shift now, mean shift vector. So you continue to repeat that. Then finally, you kind of like shift to more to the center of the data sets there. And this is like an kind of example. If you do parallel, you have like for each of these, for example, like you can for each of the data point, you can think of like that style, each of the data point. Okay, in the simplest case, each of the data point you can start a cluster, right? And then all of them, you let them to go for this mean shift procedure. Then, like in this example here, in this data set, they will eventually all merge into one center there. So therefore, like all these data points are supposed to be in the same cluster. And for example, if outside maybe there's something else, maybe these points here will be will eventually move to other clusters, so that will, converge to other clusters. So these points here in yellow will be belongs to other clusters. And this is just another illustration for that. So you have start with data points here. So therefore, it's quite laterally forming two clusters. So it's actually pretty nice. It's actually a little bit similar to what we're going to talk about. It's a Watershed algorithm, where it's similar, but it's not have that kind of similar flavor, but not completely. Then to use that for segmentation would be kind of the same idea, right? So you just need to specify the features in that dimensional space. Then you start doing this mean shift. But of course, apparently comparing to k-mean, for example, will be quite a bit high complexity. And this is some of this mean shift segmentation result, and more result here. Yeah. And as I mentioned, if you're trying to take each of these pixels as a center, like cluster center at the beginning, it can be very computationally intensive, right? one thing we may do is we can start with like, of course, I'm not using all of them as the cluster center, and also like, let's say just go for one of them. When you go for one of them, we can, let's say we start with one of this guy here. As you go along to find the mean shift path, we can exclude all these points here because all of them should be also belong to the, you expect all of this should eventually fall into here, right? So therefore, like once we do that, we don't need to look into this guy anymore. So if we start from here, like we go through this path, like all the way up to here, then we can exclude all these points here in the middle. So maybe then we start from here again, like we go through another, like maybe it swap again, like all these points here, then we can exclude all these points in the middle and so on. So I always find it very tedious to look into these pros and cons. I will let you to look at that. But one thing is obvious that like it's computational quite a bit more intensive than what we talked about earlier, like for k-mean. So do I have? Yeah, actually I don't have any of this. I don't think I have sample from mean shift. But anyway. So next thing, like final thing I like to briefly go through is like the superpixels. So as I mentioned, like, so yeah, it's kind of like a segmentation, but it's kind of over segmentation. That's the concept actually proposed just rather recently, just a decade or something ago. So it's kind of like have some wait a second. As I mentioned, some of this potential application. Honestly, I don't see too much. Maybe I didn't really dig much into that. But potential application is if you have a very fast mean shift superpixel algorithm, then instead of processing each of these pixels, you can pixel like individual unit like superpixel. So potentially you can decrease the complexity of later algorithm quite a bit. And also actually we know how to do superpixel for a long time ago because for example, Watershed algorithm is a very old algorithm, and actually I will talk about that later on. Maybe I see you guys are all almost falling asleep now. Maybe I will just show you some demo or something. So let's say here is some a Watershed Watershed card. It's doing segmentation. Okay, I guess maybe I make the number of segments. Let's see, how do I do that? Let's see, D. I think I changed this D or something. Oh, this is probably very fine. Okay. That's more intermediate, but as you can see, it's super quick, right? This thing here, you do this over segmentation very quick. Then potentially, if you have over segmentation for this guy, if you want to do better segmentation afterward, you just merge some of these regions there. You found very good segmentation, right? And it did create the boundary pretty well. It kind of follow the boundary pretty well. So. So let's look at the Watershed algorithm here. Yeah, I don't want to go into this disable. Okay, but one thing is apparent, right? If you have this superpixel, at least you want to the boundary kind of really have a good alignment with the actual boundary, right? So that's obvious. There's a number of like potential algorithms there, but I only will talk about like tools to like Watershed and Slick here. So Watershed is a very simple idea. So it's just as the name suggests, you can think of like physically. You can think of like your image is kind of like a valley. So if you think of like three-dimensional, then the darker region is like like a basin, and then the brighter region is a higher part. Then think of like if you fill water like from bottom up, then you slowly you will kind of like apparently you will get like segment out like different parts, right? For example, if I keep filling up like from bottom to up here, then laterally I found like several like segmented regions here. As I fill up the entire image, and as you go up here, it will spill to the other side. But if I build a dam here to just continue to keep them apart, then this dam here is called the watershed line, basically. And this watershed line is basically the boundary of your segmented region. And look at the simplest. Okay, look at this simple algorithm with the watershed line first. Like, I mean, as I mentioned, what we are trying to do is just imitate like what was going on for this previous picture here. Right? Just trying to like think of like your water coming out like from the ground and then slowly like filling up and so on. So then what we can do is like we can start with some maybe lowest points, but honestly it doesn't necessary to be those points. Think of like you start with some local minimum and continue to fill up there, and those will be our seeds there. And starting from those seeds there, we'll just put all these seeds into a priority queue. And basically, like the seeds, like when they have like smaller in density, they will have lower priority because you want to fill from like bottom to up, right? From lower sea level to like higher sea level. Then you just draw from this priority queue, right? So you draw from basically the pixels that has in the sense will be like already in the queue but has a lowest level, right? And you draw there, you just put all of this to be, let's see. Okay, I guess yeah, and then like some of them, okay, you draw in the queues, but some of them probably is already processed, right? So, but some of them are not processed. So for all those not processed like pixels, labeling pixels, you will just put in the queues again. So for the unprocessed one, for the already processed one, you don't care, but the unprocessed one, you will put in the queues. Then you continue to draw it like this. So maybe I don't have a figure here, but if you can think of it, say maybe I have like this is like the minimum somewhere here, right? Minimum somewhere here. So I basically start with all this minimum. This is the minimum here. They are all put in the queues at the beginning. Now I start with the lowest one. So maybe like this have a lower sea level than this guy. So I start with this guy here. Then I put always labels that is not processed yet into the queue. And I draw out that itself. So this is now gone, not in the queue. Then next time I will continue to like pull things from the queue. Right? Now these 4 pixels here, and this guy is in the queue, right? But if this here is still lower than this guy, I will continue to work on this one here, right? Then again, I will just like put the unprocessed one in the queue. Then I have this guy here like in the queue, and then just continue. So it's just trying to imitate this word. I don't know how to. It's like a spring kind of like flowing from the ground, that kind of like process. But note that like this one, the simplest one does not like create a watershed line. So we can modify a little bit to create a watershed line. So again, like more or less we can start with some seeds there. Then again we will put seeds and always labels in this time. Like we will first put all the system, the labels, like in the particles first. And again, like, of course, like the labels, we just have the sum. Okay, I guess I probably have a mistake here. I don't think this is necessary. So basically, put itself and all its labels to the particles. So I sit and itself in the particles, and then like everything is considered a wet or like process. Then now again you draw from the minimum, the lowest point there. But then like if not all of its label is already wet, then you will just put that back in the queue, and also like you add all the unwet labels to the queue with its marker. Otherwise, you will just say, otherwise you can pull that process point out of the queue. But then like, so actually it's like this kind of situation. Something like if you have a point here, you have a competitor, something here. Maybe my competitor is too far away. But anyway, like as it goes closer and closer, maybe something like that. So this is the same cluster, right? So what's going on if like maybe I put them. Okay, it's hard to have. It's not very convenient to have different colors. Maybe I just check like that. This will be one cluster, right? And this is another cluster. And now if I have, considering this guy here, if this guy, if all its label is not, let's say, like if this is the lowest point now I'm considering, if all its label is already like wet or like is in the queue somehow, then there will be a two situation, right? If this is already like if one of its label is like belong to a different cluster as itself, then I know this guy is actually at the watershed line, so therefore like I will just mark it as a watershed line. Otherwise, if for example if I have, considering this pixel here, if this pixel, because all its four labels here is belong to the same cluster, so it's not in the watershed line and so on. And also like if I'm actually running on, I cannot do undo anyway. So if I am working on this pixel here, somehow like its label is not processed yet or not wet yet, or not in the queue yet, so I need to first put them in the queue or something. So then I'm also like myself will just put it in the queue as well, like put it back into the queue. So anyway, like if you have the basic idea is not you can just like make different variation of the watershed algorithm. Honestly, there's lots of different variation of this algorithm and like over the years, but it's like a pretty kind of old algorithms as I mentioned. So I don't know why this is not moving up, but so of course you can some of this simple trick, for example, like by nature you may have more kind of like boundary lines than you want, but you can, for example, first smooth out the image a little bit before you applying that, then yeah, I probably pull up a little bit. I don't know why it just suddenly pull down. Then you can able to reduce the number of regions there. And And finally, just like to mention another algorithm is called slick. So it's kind of a pretty simple algorithm for superpixel. So it's more or less actually it's very similar to k-mean. It's just it do k-means again like it's like k-mean actually more like mean shift than k-mean in a sense, because it basically like in mean shift like you have maybe a circle region or something like that. In this one it's basically just fix your neighborhood to be like you start with like let's say a neighborhood you set the seed for S, so basically like you what should I say? Let me draw it, it's better. So you start with the entire image, right? Then you just need to just make it a grid like that, and then this will be your initial superpixel basically, just from the entire grid here, and then like for each of these inside each of this square here, we just consider the 2S neighborhood there. So basically here, and then compute the k-mean. So then you basically you have your central, and then like you can with your neighborhood there to with your labeling guide to consider whether it's belong to the same cluster or like not the same cluster. So therefore, like as we iterate, you will see that like the neighborhood will change a little bit, right? Instead of like starting with a square, it will slightly distorted and get different shape, and that will form your super pixels. So the advantage in this case, I guess, is like the shape will be more regular, as you can see. Like this is example here. And it's kind of compact also. It is kind of fast, but honestly, I think probably not as fast as Watershed. But I actually have an implementation here, but it's not a good comparison because this Watershed I can find the library. It's like OpenSeries library. OpenSeries library apparently is like the best optimized. Very much optimized compared to like even NumPy. And this one I dig up quite a bit. The only implementation I can find that can be easily applied is using the scikit-learn. Scikit-learn is like quite a bit slower, honestly. So as you can see, this one here, this is the slick, and it depends on your case. I would say like it is for this one is I don't know, like it's because of the implementation or whether the algorithm itself. I'm actually that's also one of the let's see, maybe like I'll show you one more things, then we will just go OpenCV, there's only one of these. Oh, I think I need to source it first. You have another algorithm, like it's a newer algorithm for superpixel, and this is yeah, if you're interested, you can look into that. Also, this is quite fast, but I cannot say whether it's actually much better than Watershed or not. So you can see, but at least in terms of just computational complexity is fast. Even though like OpenCV also have this slick implementation. As I said, like, I couldn't make it successful. I couldn't see any people like online did a illustration of using that function in Python. Like, even for I cannot find an example for like C++ implementation. So definitely, yeah. I didn't try that one. So, but that's basically like superpixel. So okay. I guess I'll just stop here, and then I'll see you guys next week.